1854, Göttingen. A young mathematician seeks to obtain the position of assistant professor at the University of Göttingen. To achieve this, it is required that he publishes a thesis, which will be evaluated to determine whether he is suitable for the position or not. This young mathematician, whose thesis advisor was none other than Gauss himself, publishes what will become one of the most influential works in contemporary mathematics, on the hypothesis on which geometry is based, his name Bernhard Riemann. As Newton rightly asserts, we are dwarfs standing on the shoulders of giants. Although Riemann will go down in history as one of the giants of calculus, in his time he was also a dwarf who had to climb onto the shoulders of past giants to glimpse new light. Therefore, to better understand this story, we need to go back to ancient Greece, as during that period the basic ideas and concepts were established for our young mathematician to the field of geometry and calculus. Classical Greece. Eudoxus of Cnidus formulates a method for calculating the areas of figures by approximating them to polygons. Later, Archimedes perfects this method by applying it to quadrature problems, constructing squares with an area equal to that of a given figure. Let's return to Göttingen in 1854. Our young mathematician will generalize these concepts by defining the Riemann integral, a concept that allows the calculation of the area under a curve by summing the areas of rectangles defined in a partition of an interval of the function. Let's suppose we have a function fx whose graph is shown here. We want to calculate the area between point A and point B under the curve of this function. How can we then calculate this area under the function's graph? Riemann's idea is not to calculate this area directly, but rather through an approximation based on the sum of a series of figures whose area is easy to calculate, such as rectangles. For this task, we will divide the distance between point A and point B into a series of intervals of length delta x. We will take these intervals as the basis of the rectangles, while the heights will depend on points on the graph. Thus, the approximate value of the graph will be equal to the sum of the area of these rectangles. In this case, where we have divided the graph into 5 rectangles, the approximate area of the graph will be equal to the sum of the area of these 5 rectangles. These rectangles have in common the same value for the base, which is equal to the absolute value of the difference between the points defined as endpoints, divided by the number of rectangles to be constructed, which is 5. Therefore, delta x is equal to b minus a divided by 5. For the height of each rectangle, we will choose the values of fx for the highest x in each interval. This formula, with all the variables we have, can be compressed into a new formula that consists on the summatory of all the rectangles that we have created, so now we can calculate this area of the graph. So in this case we have all the rectangles starting from rectangle number 1, A1, to rectangle number 5, A5. But what if we want to use more rectangles to calculate the area of this graph? This expression can be generalized substituting the 5 from our summatory to n, so we can calculate the amount of triangles we want to approach this area of the function. The more triangles we use to calculate this area, the more precise will be the calculations of this area. So this is why we change this formula and set a limit to infinite to calculate this graph. This is what it's called the sum of Riemann, fundamental to understand the integrals. The Riemann integral, an extension of the Riemann sum, has essential application in mathematics and physics. It is used to calculate areas under irregular curves and volumes of three-dimensional solids by dividing the region into sections and summing the areas of rectangles. In probability theory, the Riemann integral defines the probability density function, allowing for the precise determination of probabilities in intervals. Additionally, it plays a key role in dynamic systems by modeling phenomena evolving over time, such as calculating work in physics or solving differential equations to study the accumulation or loss of quantities over time. The versatility of the Riemann integral makes it a fundamental tool for understanding and modeling complex phenomena across various scientific disciplines.